Okay, good morning, everybody. Hello. Thank you very much. So welcome to the session. Today we're going to be talking about cloud optimized data in EOSDIS. We're going to have 3 talks. I'm first up. My name's Owen Littlejohns. I am the Transformation Train Architect on the NASA EED contract, and I'm going to be talking about Zarstores in NASA's EOSDIS. After that, we have Dumai from JESDISC, and she's going to be talking about persistent Zarstores and how we might update them as the data change and are updated themselves. And then last up, we have Aaron Fries from LPDAC, and he's going to be talking about cloud optimized geotips. So yeah, Zarstores. What I want to do today is firstly talk about why we might care about them right now, and then what are Zarstores, and give an example about how within EOSDIS we can generate them. I'm going to discuss a little bit about the on-demand case for Zarstores and how we do that right now, and also discuss what persistent Zarstores and what that might mean. And there's a lot of open questions there. And then I'm going to wrap up with a lot of open questions. So it's going to be quite unsatisfying on my last slide. So right now, as everyone probably knows, NASA is in the midst of migrating a whole heap of data to the cloud. And so you can see up there, I had a quick look on Earth Data Search, and there's currently in the cloud, in production, over 1,000 NetCDF4 collections. And then there's about 150 geotiff collections. I actually checked last night, it's 155. But as we move all these data to the cloud, and as our future looking missions are looking to just put things natively in the cloud, it's a good time to ask whether the formats that we've been using for a long time are still the right things to be storing our data in. As we have these things in a new environment, is there an alternative way of storing those bits of data in a way that we can gain performance benefits when we're doing analysis and can ultimately do things better for the end user and for science? So 2 of the options, and I've already mentioned these. So Czar, which is what I'm going to go into gory detail about in the next sort of 15-20 minutes. And then also Aaron's talking about COGS, as I've mentioned. So what is a Zarstore? So the easiest 1-sentence thing I can think of is just imagine like a directory store of your data. Instead of having a single file where just you have variables all contained up in like a single container, you've got like arrays and you've got metadata associated with those arrays. Instead, you express that as a bunch of different objects somewhere. It doesn't have to be the cloud. It's good for the cloud, but you can do it on your laptop. You can have this anywhere. You can have like a directory like structure, your laptop, a Docker image, anything, you can have a Zarstore. And so what it does is it expresses these things that, for example, you might have in a NetCDF4 file, these n-dimensional arrays, and it uses an open source spec, but instead of being this more traditional file format, it's tried to be designed specifically to allow efficient input and output, which is great. Like if you combine this efficient IO with an environment that allows you highly parallelized computing, you can do really efficient workflows and you can do them really quickly. So you can do either more science in the same time, or you can do your science in a less amount of time. One thing that's really nice with Czar as well is that it is compatible with the right metadata in your Zarstores with tools that the end user is already familiar with. So you can use your Zarstore with something like Xarray. And so we don't have to really change how an end user might be interacting with the data as much. So a little bit more detail, if you're like me, okay, I've given you the top line pitch on what a Zarstore is, but what is it really? So if you have a NetCDF4 file, and I'm going to be comparing to NetCDF4 a lot in the next few minutes, it's a container for lots of variables. So you have this file, and inside it, you have a bunch of scientific measurements. I kind of already said they're represented as an n-dimensional array, and it has metadata in sort of key value pairs. And that's what we have in a NetCDF4 file. Instead of taking that same container and having it in one place, that array is split into chunks. That chunk is essentially a portion of the array, and that is written out in a Zarstore as a separate object. And so we have a whole bunch of files instead. Alongside those chunk files, we also have metadata files, and this is JSON. So all of those metadata attributes you're used to seeing in your NetCDF4 file, they exist in a JSON format file next to the chunks for that variable. And again, talking about NetCDF4 files, they can have multiple variables in them, and those variables can be in groups. So you can hierarchy inside your file. That can be represented in Czar as well. So essentially, each variable is a subdirectory. And inside that subdirectory, you have your chunk files, you have your JSON with your metadata, it's all grouped together. If you have groups, that's another directory. And so all of your variables inside that group are subdirectories inside that group directory. So it's just a massive directory structure. And then, to save time and optimize for things, if you have an array that has a whole bunch of fill values, which obviously happens, you don't need to have a chunk for that. You have all the metadata that tells you, hey, this is my fill value. I'm not going to bother making a chunk for that entirely filled part of the array. So again, like a more visual example, and this is me being very dull and getting a screenshot of my terminal. This is part of what a Zarstore looks like on your file system. So at the top in the blue, that's the root of the Zarstore, that .zar. This is a PODAC collection, I think it's an echo collection. And you can see within it that it is a directory tree, right? Those other blue subdirectories, those are each variables. And then within each of those variables, you've got these 3 files. There's the 0.0.0, that's a chunk. And the reason it's got those 3 zeros is it's a 3-dimensional array. And so it's telling you it's the 0th chunk in that dimension, the 0th in the next, and the 0th in the next. And the reason this is a very dull example is it turns out that actually those variables are really small. And so you only need 1 chunk to store it, which kind of makes it a bad example. If instead, let's say we had 3 chunks in that last dimension, you'd see 3 of those numerical file names. There'd be 000, 001, 002. And then kind of the magic that happens is in that Z array file. That tells you, hey, you care about these elements in the array, you need to open up these chunks. And so you're only opening up the chunks that contain the data you care about, which ultimately means you can read less data to get what you want. And then that ZATTRS, Z attributes, that's that JSON file I mentioned that contains all those metadata attributes. And then for a Zarstore that has multiple variables, there's that Z metadata file right at the top there. That's a consolidation of all of the different metadata for all of the variables. So you have like a convenience place for just that, all of the metadata without having to peruse the whole directory structure. So we have a number of ways that we can generate Zarstores, and I'm going to focus in on one that I know a little bit better. So this is a Harmony backend service that is called NetCDF to Zar. So the clue's in the name. We take NetCDF4 as an input file format, and we create Zar output. I'm going to assume that not everybody in the room knows what Harmony is. So very briefly, Harmony is it's a whole ecosystem essentially of different backend transformation services. So the idea is that different service providers publish a service as a Docker image. So this could be something that temporally subsets, reformats, reprojects. Oh, that's exciting. Somebody doesn't like Harmony. Somebody really doesn't like Harmony. This is really fun. Okay, so Harmony. So we have all these Docker images, right? And they all do different types of transformations. What Harmony will do is present like this consistent API that an end user can make requests to, and that can access each of those different transformation services. So, you have this one consistent OGC inspired API. You request things in the same way. It doesn't really matter if your collection supports this service or that service. You're going to kind of ask for the same type of API request. And then once you make that request, Harmony has some logic which says, okay, you've asked for this collection, you've asked for these options. I know to send it to this backend service. And in our case, it's the NetCDF to Zar service. So the service can do a couple of things. It can do essentially a one-to-one, one NetCDF4 input file to one Zarstore transformation. Or one thing that's perhaps more interesting and more useful is it can aggregate multiple NetCDF4 files into a single Zarstore, which is kind of powerful. Like it doesn't necessarily buy you too much if you've got small, like 10 megabyte NetCDF4 files and you convert them into a Zarstore one each. But if you have thousands of those files and you make them into a single Zarstore, then that enables much more powerful analysis downstream. So I have, gosh, a URL for a Harmony request. If you are wanting to use Harmony and you're not yet familiar with it, I would recommend using Harmony Pi, which not only looks better in presentations, but it's a much more intuitive way of making your request. It's a pip installable Python package. You can define your request options in quite a more sort of straightforward way. And if you're used to using things like Python and Jupyter Notebooks and all those kind of analysis tools, it's a really nice way of doing business. But looking at the anatomy of that URL, you can see firstly, obviously, it's going to Harmony. It's specifying the collection. This is a PoCloud collection, so it's one of Podak's collections in the cloud. Towards the end of the second line, wrapping around to the third line, it's saying what the granule I care about is. So this is a request for a single granule in that collection. And then at the end, it's saying format equals, it's essentially the MIME type of Zar. So it's saying, hey, I'd like a Zarstore for that one granule in that collection. Once the backend service has processed this and produced the Zarstore, Harmony does its standard thing of dumping the output into an S3 bucket and then giving the end user a stack output with the URL to that product so that the end user can access it. And the best way really to interact with the data once you've produced it, because this is one of those cloud optimized formats and we have like so many files in there, it's really the best thing to do is to use it within the cloud. So you might want to use something like the OpenScapes 2i2c hub, because that's also in the US West 2 region where the output data are hosted. You could download it with something like the AWS CLI if you really want to, but it makes sense if we're making like a really big Zarstore that aggregates a lot of files, like let's keep it in the cloud and let's do the analysis in the cloud. A maybe more interesting example is you can aggregate. I've mentioned this already, and the picture kind of really shows what we're doing here. We have 6 input files. They all have the same grid with respect to latitude and longitude, but each of them represents a single half-an-hour time slice. So they're essentially latitude by longitude by one time element. And so instead of having 6 files with those dimensions, we can create a single Zarstore that has the same latitude and longitude dimensions, but a time dimension that's 6 elements long, and just have the one Zarstore. And then you can do, say, time series analysis across like a specific spatial location because it's all in one place and it's really easy to get at. This figure was taken from our NetCDF to Czar GitHub repository. That's on the NASA GitHub organization. There's a Jupyter notebook in there if you're interested for some more examples. It also has Harmony Pi code, as I've already touted. It's really kind of the best way, I think, to programmatically access Harmony requests. If you prefer to make sort of UI-based requests, then you can make them via a data search client as well. So that's another alternative. So a little bit of information about how that aggregation happens. So first up, we kind of need to know what the output Zarstore should look like dimension-wise. If we're taking, I don't know, 150 different granules, we need to know how many time slices each of those granules has, so we know the size of the output Zarstore. And so once we have all that information, we create this empty store. And then there's this kind of interesting thing that we realized, thanks to help from JESDISC, in fact, it's really bad to write partial chunks. So that's when you have, your chunking doesn't necessarily match the size of what you're trying to write out. And so you maybe say have half a chunk that you want to write out. So maybe you can write it well the first time, but then the second half that you're writing, you have to read all of that back in and then update it and then write it out. And that's like terribly inefficient. And can make your service really, really slow. So to avoid that, when we're initially doing the write, we sort of base the chunking around the input granule sizes. And then once we've got that performant writing done, we use the Pangeo Rechunker, which I think Ryan Abernathy was involved in. And we use that Rechunker to make our Zarstores actually more performant for reading afterwards. Because having these things that are chunked sort of how the input file is kind of isn't really optimal for reading, it's only optimal for writing. And so because we don't know how the end user might be trying to use the Zarstore, we sort of compromise and try and make something that is okay for each of the dimensions. So, we try and balance it so that there are approximately the same number of chunks in each dimension, rather than specifically saying, hey, we want this to be really good and performant for time series analysis. So by not being amazing for any single given dimension, it's also not terrible for any given dimension. We do try to speed things up with, parallelism. So we have a process-based parallelization within the Python code. I've already mentioned that we try and balance the chunking scheme so that each dimension is okay. This Harmony backend service right now does kind of hit limits when you try and process very large amounts of data. For example, you wouldn't want to transform an entire collection with this service right now. But if your use case was, I have 50 granules, then you might want to consider this. Another sort of performance hit is like that rechunking is actually quite an expensive process for these big Zar stores. It can dominate the runtime of this service. A couple of other sort of quick points. We don't yet spatially aggregate. So if you have a collection that is tiled and maybe you want to have a single Zarstore that not only is stacked in time, but you want all those tiles to be together on a single grid, we haven't yet implemented that. There's work in the backlog to do that, but it's not yet been done. And we're not the only people in this realm. There are recipes on Pangeo Forge to try and create these Zarstores, and they're doing some really cool stuff. I think they're using Apache Beam. And there's obviously an overlap between what we're doing in Harmony and what they're doing. So we should really try and work out what the respective niches of those tools are and whether we in fact need both of them. I think that is a good and valid question to ask. So switching gears a little bit, that was on demand. That's my user saying, hey, I need these data. I need them in a Zarstore. I don't care what's already there. That's the Zarstore for me. Instead, you could have something that you create upfront. And this is more akin to things that Giovanni does. So you have a collection, you have variables in that collection, you make the Zarstore once, providing that it's a stable collection that isn't having more data added to it. And then you say, hey, users, here's your Zarstore. You don't need to make it. We've got it for you. And that's, on the surface, like you're creating it once. You don't have 100 users trying to create the same thing. That's great. But, there are other implications, like there's the duplication of the data, like a whole collection can be, petabytes, maybe, certainly terabytes, if not petabytes. And so particularly with some of these big missions coming up, like SWAT and NISAR, so you have to pay to host it twice. You've got your NetCDF 4 version, but then you've also got your Zarstore, because I think at this point, like, I don't think anybody's ready to say Zar is the only way I'm going to host my data. And sort of similarly to some of the things I was saying before, okay, we're going to create a Zarstore for the whole collection, but what should the chunking look like? Because this user wants to do this thing with the data, but that user wants to do something else, and the chunking doesn't work for both of them. So does that mean we have more than one Zarstore because we need more than one chunking scheme? So we're paying to host 3 versions of the collection? Like it's, there's a lot of questions there. And also, if there are multiple ways to access the data, we need to make sure that it's really clear to the end user which one they should use for what and how they get at it. So we need good metadata, and it needs to be easy to discover. And then sort of a bit of a teaser for the next talk, like these collections aren't always sort of static and fully processed. There are new data coming in for some of them. So how do we make sure that we can add those data so the end user is able to get the most up-to-date version of the collection? What if they're trying to do some kind of real-time analysis and they want the data that came in 2 hours ago? So a very quick maybe comparison between these 2 types of Zarstore, on-demand and persistent. With on-demand, we can make what the user wants, providing we have an interface for them. They can ask for something, we can make it, and we can only make the thing, that they want without making anything else. And that's good. If they only want 50 granules in a Zarstore, we can do that. They don't need the whole collection. And in theory, we can make it so that they tell us, this is the chunk scheme for me. I want to do this type of analysis. These are the chunks that are going to help me do that. Please make it look like this. Problem is that you can have 100 users asking to create a Zarstore of all the same data. And so, we can have very, very similar Zarstores that exist in tandem with one another. Alternatively, we've had the persistent example, and it's great. Make it once, providing you don't have to update it. And it's a good option, I think, for whole collections. But as I've said, that chunk size, like, it's not one size fits all. So that's not necessarily a great answer either. So I think there are use cases where one of these suits better than the other. So my last slide that's with disappointing questions. We don't have all the answers right now. As this are thinking about this, there is a draft RFC talking about how to adopt Zar version 2 as a standard format for cloud hosted data. Question sort of about whether we need on-demand Zar. So going back to that last slide, when is it that we actually want to be able to say to an end user, yeah, sure, you can make a Zarstore. And I think that right now, sort of the short-term answer to that is we don't have collection-based Zarstores for every collection, so we need to be able to bridge the gap. But going beyond that, if there are these different types of analyses that require different types of chunking, there's a use case there that says, well, an end user probably might need something specific to them. And then just sort of to mention again, I think we do need to be comparing the different things that can make Zarstores on demand to make sure that, we're consolidating our efforts, and, each of these different tools, if they all exist, they have a well-defined niche and they're serving a well-defined purpose. Yeah, that's all I've got. Any questions? There's a couple behind you. Oh, there's one. You have one in oh, one in chat.
Nice talk, Owen. I just was curious about so with the NetCDF to Zar service, I guess the advantage to having a Zarstore is that you're just like streaming the parts of the data that you need, but the data has to be living somewhere. So when you if there is like a continuing on-demand Zar generation service, then how long does that Zarstore that was created last in the place where it was put on S3, and the user can keep using it? Or like what are the ramifications for then having things that need to be continually hosted in addition to the original data format?
Yeah, that's a good question. So I mean, right now, specifically with Harmony, things that Harmony produces and puts in its own staging bucket, they get cleaned up. And I think it's I want to say it's every 30 days. But I think this has been implemented. If it's not, it's like very much in the pipeline, the ability for an end user to say, hey, this is the bucket I want you to put the output in. And so you could say, I want it in my bucket and I'll keep it for as long as you want because you're the one paying the bill, right? Yeah. Yeah.
Hi, Owen. Dave Jones with Storm Center Communications. I didn't understand a single word you said, but that's okay because that's not my reason here on Earth. I'm just wondering how you define a user. And once I hear that answer, I'll have a follow-up question.
Yeah, that's a good question, and we've been having some interesting discussions about that over the last few days. I think that there are a lot of different users. I certainly think that, there's scientists, obviously. I think that, there is a broad variety of end users, whether it's sort of disaster response, things like that. And then, but I think, scientists are a broad part of that.
Yeah, I just placed myself in the last mile section where we access and deliver data to decision makers, to people who have to not analyze the data but trust it,
right,
and move on with decisions that they have to make, and sometimes pretty quickly. Does this approach that you're talking about, does that ultimately lead to providing like web services where we can make calls with interactive GIS platforms to pull the data that we need out of EOSDIS and deliver it to customers across their platforms?
So I think it does enable things like that. And I think Giovanni is a great example of something that is backed by Zarstore. So you can make requests to Giovanni to do like time series analysis and things. And so, I think it does enable more use cases in that way. Yeah.
Thank you.
Yeah.
Hi, this is Hailiang from JustDisk. I'm very excited you're using Rechunker. Just like I know Rechunker is a very smart implementation, but they do have some parameter to tune, like the intermediate storage, right?
Yeah.
So that's a balance between storage and performance. So, and probably Harmony under the hood is still, I assume it's still running Kubernetes, right? So the service. Yeah. So basically, I think lots of factors you need to consider, like how large is your part, and also like how do you choose the intermediate storage? Any advice for other people?
Yeah, that's a good point.
I just wanted to put in a plug for Kerchunk.
Yes, that's fair.
Because there's no advantage to the user over reading Zar files compared to NetCDF files if they have the same chunking when you're using Kerchunk. Right. And so we actually use Rechunker to rechunk the data to Zar, and then we convert it back to NetCDF files. Because it serves a wider group of people, and then you don't need to do the duplicate file thing. So you end up with just rechunked NetCDF files, so that then you can use Kerchunk to get the same performance. It looks like a virtual Zar data set, and you get the same performance as if you stored it in Zar format.
Gotcha. Yeah, that's interesting. Thank you.
Do you agree with that, actually, or?
I knew about Kerchunk, yeah.
Yeah, and I'm going to do the same thing of PangeoForge. So the comparison study between NetCDF to Zar and PangeoForge, I'm not sure if that's needed at this point, because yeah, I'm wondering why not just adopt PangeoForge even with the implementation to Kerchunk. So those limitations behind like not being able to chunk in what space but not time, like that community has been able to sort those things out, and you'd have the advantage if Harmony just adopted PangeoForge of having people outside of NASA contributing and helping figure out some of those limitations.
Yeah, I mean, absolutely. And I think sort of very much say in the light of, I haven't looked at the comparison, so definitely something interested in, and like community engagement is, I think you're right, that's huge.
Yeah, so you said that the Harmony API was OGC inspired, were the words that you used. And so I was wondering that presumably that means that you're actually not compliant with OGC APIs. So in what ways do you depart from the OGC API standards, and why?
That's a good question. So we have coverages endpoint. That's like kind of the main sort of endpoint. That's to sort of do, range related requests, subsets and things. I think that the main departure is that we have some additional query parameters to allow you to make additional requests. I don't know that they are specifically in the spec. Okay. Okay. All right. Let's see if I can find the chat. Okay. Okay, so I'm seeing a question from Micah about retention period for outputs from Harmony. I think I covered that already, but I think it's 30 days if you don't specify your own bucket. So that's how long it will stay in the Harmony staging area. And do we have per use limits? So Harmony has been designed recently or redesigned to have no granular limits is sort of the phrase. I think the NetCDF to Zar service is kind of the one exception, because it allows you to try and aggregate a lot of data, and it gets to a point where it can't handle it. But generally speaking, you should be able to request as much as you want through a Harmony request. I think that was all the questions. Okay, so sorry about running over.
Hello. Apparently we're not supposed to block hallways, so if you're standing, maybe if you can find a seat. Thanks. Hi. Yeah, slideshow. Okay, I think we're going. My name's Christine. Dumai and I are going to be talking about managing data sets that change, because most of our data sets at NASA do change. We are both software developers at NASA's EOSDIS, which is one of NASA's Earth Science data archives. So I'm going to kind of set up the question, and then Dumai is going to talk about some work she's done to look into solutions to this particular problem. So the way we have sort of traditionally done things at the archive is that, you know, we're at the archive, we have these servers, they're sitting on premises. And as we get data, we put data into those servers. And when our users come along, they, you know, they find this data and then they start downloading it, and they download and they download. And then, you know, maybe they run out of space because our data sets keep getting larger and larger. And so then they sort of download and download and download some more. And finally, at some point, they have their data, which is fabulous. And at that point, a lot of times they're like, okay, I'm done with the archive. And so now they do their analysis locally on that local copy of the data. But while they're doing that analysis, we at the archive, we're getting more data and we're putting it in our servers. But our users, they're not seeing that new data. And sometimes that's okay. Maybe like your area of interest is not getting new data, but you know, sometimes we have to put in corrections in the data, for example. And so you may be doing analysis on data that we know actually had a little bit of a problem with, and you're not seeing that new data. So there are some downsides to this style of access. The download can sometimes take a lot of time. It can take a lot of disk space, depending on, you know, what data sets you're trying to access. And then the data can get out of date very quickly. So, you know, the new world that NASA's been talking about over the last few years is where you do this in-place analysis. So rather than Paul putting data into local servers at the archive, instead we at NASA, we went with AWS, and we store this data in buckets in the cloud. And so now when our user comes along, instead of downloading the data, she spins up some kind of compute in the cloud. And now when she runs whatever she wants to do in the cloud, she's accessing that data right from the cloud, right next to the cloud. And so as she runs, right, if Paul comes along and he needs to update something, she sees that update immediately. And so there's a lot of advantages here. We're no longer downloading the data. We're right next to it, so we don't have to download it. It doesn't take a lot of time, because if we're going to download something, generally we're going to sort of download our results. We're not going to download all the source material. And the data no longer goes out of date. We take care of making sure that data stays up to date. So this is great, except, right? Otherwise, this wouldn't be an interesting presentation. Okay, so let's sort of reverse and let's look at this picture again. So a lot of times when you're dealing with data in the cloud, you are reading this data multiple times. And if the data is in some kind of cloud optimized format, that first read that you do is a metadata read. So you read the metadata, and that metadata tells you something about the structure of the data in that object. So if Paul comes along and he updates that object after you've read the metadata, and then you try to access the data out of it, potentially that will cause problems. Like if the shape of the data changed, if the variables in the data set changed, something like that, you can suddenly have this failure. And then you can kind of be like, well, that was weird. What happened there? Let's try this again, right? And like the second time you come through, you can't replicate the problem because now the data is the same. It didn't change that time. So at that point, okay, you can't, okay, I didn't realize. Let me see if I can get this out of the way. Can I minimize? Thank you. Okay, sorry. Okay, so at that point, our user's kind of like, well, why did it work that time, right? And it may even be that it doesn't fail, but you get odd results, which hopefully you will notice, but you might not, or you'll just come back later and the result you got yesterday is not the result you got today. So the fact that it stays up to date is great, but there is this downside to the fact that the data is sort of not consistent and it's changing under you potentially as you are doing your analysis. So now we're going to narrow the focus and we're going to talk about Zar. And Dumai is going to talk about some solutions we've looked into that address this particular problem in Zar, although it is kind of a more general problem when you're working right next to data that's changing.
All right, thank you, Christine. So Owen already gave you a really nice introduction to what Zar is, so I'll just jump right in. You can have a Zarstore in some kind of cloud storage system like AWS S3, and it's static. You write it once and the user can just access it if it's open for access. But given the nature of our earth science data, where we frequently get new information like a new time slice to append to the existing data or update something in the middle of the existing data, then we need to consider dynamic Zar stores. So let me continue with the Paul and Amy cartoon to demonstrate kind of the potential issues that could come with a public dynamic Zarstore. So Paul, our data manager, let's say he has in the cloud AWS S3 a Zarstore, and that Zarstore contains an array of shape, say 180 by 360 by 504 for latitude, longitude, and time dimensions, for example. The chunking scheme is something like 10 by 10 by 100. Amy, our data user, again, wants to do some kind of calculation with Paul's Zarstore in the cloud, like pull out a time series, for example. And she has a few independent workers that access different chunks at different times. So that looks all simple and good, but this is a dynamic Zarstore. So Paul will get a new time slice to append to. So 504 there needs to become 505. So he needs to update the metadata and the 18 by 36 chunks in latitude and longitude. And S3 doesn't, as far as we know, doesn't allow all these chunks to be written simultaneously. So as Christine mentioned before in the general setup, if a user is trying to access it during this update process, then we're going to have some issues. So Amy is that user, for example, and some of her workers will read the metadata before the append update. Some of them read after, and same with the chunks or the raw data. They can read it before the append or after the append. And as a result, we might get, or Amy might get inconsistent shape information or weird answers for her calculation code. So in this case, we at Justice, and particularly Cloud Giovanni, were Paul, and we want to ask the question and solve the problem of how do we manage such a dynamic Zarstore to prevent these kind of issues for the end users like Amy. In thinking of a solution, we have brainstormed a few evaluation criteria. So excuse this kind of wordy slide, but first we want to be able to append new data as well as update old data, like somewhere in the middle of the data set. The user should experience minimal service interruption ideally, and the user should not be exposed to a mixture of old and an updated Zarstore like what Amy had just gone through. And some of our solutions, we consider third-party libraries. So we'll keep in mind that our Zar data won't be unreadable without the library, so we would want it to be still readable with Zar Python and Xarray. But of course, this won't be a total deal breaker if there's an up and coming library that's well supported and good for Zar onward. That library will be around for a while, of course, that we won't need any costly version buckets and no huge overhead compared to our current solution, which is the first solution that I'll talk about in a tiny bit. That parallel access is possible, meaning multiple users can access the store at a given time. and that it can handle many data updates without any performance degradation. All right, so a quick overview of the potential solutions that we looked into. We looked into how to have a partial store that is used to update the primary store, an offline period, this database format called the OCDB plus tree, and a data platform called Array Lake. So I'll talk about each of those very quickly. It won't be a deep dive, but mostly to introduce you to them and put them on your radar. Okay, so the first one is solution one, is using a partial store to update the primary store. And this is the current solution that we have in Cloud Giovanni at EOSDIS. And note that it's not public yet, as we originally designed this to be for internal use only. So the end user now doesn't have direct access to the Zarstore with this setup, but they go through our service for that. And I'll talk about why it's not public, but the two primary steps to this solution. The first one is we would update the partial store. So we have the primary store, and then say we want to update chunks, the two chunks in the middle there. We would copy them to the partial store, do the ingest process or the processing of those chunks to update and append new chunks or append new data. During this first step, the user is accessing data from the primary store only, so they're getting the old data. And then after new data has been appended to the chunks, or we have done the update that we need, then we copy back from the partial store to the primary store. So that's the second step, called update. And here the user is accessing a mixture of the two stores, so the primary and the partial store, with the new information in there. But there's an important difference there. The user is not getting inconsistent information that, say, Amy was experiencing. So what are the pros and cons of this solution? There will be no service interruption needed. The user will be guaranteed consistent data. And then we don't need to use any version bucket. On the other hand, the logic to build this up is relatively complicated. Along with that is we have to introduce custom metadata to keep track of what store the user is accessing at a given time, or what chunks need to be updated. And as a result, that make this solution not quite ideal to make a Zarstore public with. As you can imagine, we want only Zar native metadata in the Zarstore for the user, and this two-store setup requires us to keep track of what the user is accessing at a given time. So this is our current solution, but since it is not ideal, we are looking for other ones. So 3 more solutions that we have been researching and gathering information for. The next one is an offline period that's used to update the store. And it's as simple as it sounds. We take the store offline to do any updates. The user can only access the store when it is online. And it might look different for other people, but we would control the access to it by a bucket policy. So let's say, for example, we have this GPM near real-time product, and we get 2 new granules per hour. So at the end of the day, we would get 48 granules to append to our existing data or Zarstore. And using a very rough estimate that we have done before, it takes about 3 seconds per granule to ingest or process. So about 2.4 minutes of an offline period each day. So not so bad, but this would look very different for different types of data. Pros of this solution: consistent data, once again, no version bucket needed. On the other hand, by definition, this is a service interruption, and 2 minutes in my example is probably not terrible, but it could be a wide range. Yeah, and related to that is that there will be a lot more decision making for data managers. So the duration, frequency of this offline period, also considering what is too disruptive to our users related to the question of who are the users. So how do we communicate that? And as well as how do we communicate this offline period, as well as the updates that we perform to the Zarstore. All right, so the next two solutions are third-party libraries that are fairly new. Let me see if I can move this so you can see the name of it. Yes, the first one is called the Optionally Cooperative Distributed B+ tree. So let's just say OCDBT for short. It's a database format that's, and then I'll move it back. Okay, that's part of the Tensor Store from Google AI. It's a new open source Python, and I believe also C++ library that is meant for the storage and manipulation of multi-dimensional data. And the nice thing is it supports Zar natively right now. So this OCDBT database format, it's meant to be an adapter between an array format such as Zar and an underlying storage system like Google Cloud Storage. So two nice features that make it a relevant potential solution to our problem is that first, it supports versioning. So that's where the tree idea or concept comes in. There's a tree of versions, and then each version will have a tree of keys. And then it supports copy on write snapshots. So old data will be copied to some snapshot area before it is updated. So conceptually a little bit reminiscent of our solution one. Okay, pros and cons. Pros, no service interruption since it uses versioning. Consistent data, we believe, will be guaranteed for the user, and no version buckets needed. Oh, and it's open source, a big plus for us. As for the cons, this is new and probably lacking some functionalities that we would like to see as of now, like some kind of pruning mechanism and S3 support, and not a lot of examples, usages, and use cases out there. So we'll be waiting a little bit before we play with it in detail. So related to that is that we're not sure about performance in terms of user access. Say the users trying to pull out time series or a map, how would this perform with this OCDBT format? And yeah, it certainly right now doesn't support AWS S3, which is our primary or actually only cloud infrastructure. But I think this would probably change fairly soon in the next few months. All right, solution 4 is Array Lake from Earthmover, and maybe some of you are already familiar. It's a data lake platform for managing the multidimensional arrays and metadata in the cloud. So traditionally in the standard architecture there, we store both the chunk data and metadata in the object store like S3. But now with Earthmover, we still store the chunk data in S3, but then metadata will be managed by this platform. And that gives it a few major features like data catalog, supporting multiple formats. So certainly Zar, and I believe also NetCDF along with others. Access control, data governance, version control, which is relevant for our problem of a dynamic Zarstore. Pros and cons of this solution: no service interruption, consistent data, no version bucket. So very similar to the B+ tree that I just mentioned. But one big difference is that it's not open source, and that might give us some logistical challenges down the road if we adopt it as long-term solution. But in the short term, we are uncertain about performance for user access once again, but in the very short term, only because we are in touch with the company and they are letting us test out the library and perform some kind of quantitative benchmarking to compare with a baseline. So maybe in a few weeks, we'll have an update to that. All right, so in summary, the cloud offers users immediate, no download access to up-to-date data, but the cloud is not all paradise, not yet at least, and data providers need to keep this data up to date without disrupting users. So we looked into the potential solutions for Zar-related dynamic data stores. None of these solutions are quite ideal, but really exciting to see, especially 3 and 4, where the Zar space is so active. All right, and then as I mentioned, so this is all just quantitative and conceptual comparison of these solutions, but I think in a few weeks we'll have some numbers as well to compare some of them. Okay, finally, thank you so much for supporting this research that we've been doing. So thank you to the SMCE admin team at NASA, TensorStore team at Google, the Earth Mover team, of course, our Justice and Cloud Giovanni team. Hailiang and Christine thought a lot about this with me. And then thank you to the authors of my graphics and all of you for your time today.
There's a question on Zoom. Okay. So our understanding, how does chunk overwrite work in Array Lake? They actually create a new chunk in S3. And so this is why Dumai was talking about pruning, that we could end up with a huge store because we're constantly updating. So the thought is that if you could prune some of those versions, you could maybe have a monthly version or something and then daily, and keep that down to something reasonable.
There's more.
Oh, jump to the first unread message. Okay.
Oh.
Oh. All right.
I can see.
Yikes. Okay, so I guess people were hopefully able to see these slides. Okay.
I can. You can try relogging. Okay.
Okay. All right.
Okay.
So question with the updates and so forth. It's less of a concern to me when we've appended data to a collection, because it's relatively obvious. We can talk about the period of record. How do we enable and communicate at least what data has changed? And so if I did an analysis with something and now all of this is updated 3 days later, we've got a reproducibility problem here, and at least communicating that something has changed, even if we can't necessarily reproduce the earlier analysis.
Do you want to take that?
Yeah, exactly. That's one of our considerations for what will we do once we open up these public Zar stores, and then we do have to update something in the middle of the data. And that's why one of my points was we need to consider, how do we communicate that? Do we keep a public log of what we have changed, especially for people that write papers, right? They want to write exactly the data source and version that they've accessed. So yeah, any ideas kind of from your point of view as a user would be great as well.
Yeah, I mean, I would say that actually this is sort of a general problem we have, because I'm going to go out on a limb here. We have some CMR experts in the room who will correct me, I'm sure, but I don't know that you can get that information from CMR, which is our, okay, thank you. Okay, so you can't get that from our current search engine. So if you as a researcher download something on January 1st and you publish your paper, unless you've kept excellent records of what you downloaded and some of the metadata that you probably discarded, you may not actually be able to answer that question either. We do have a partial internal solution where we are looking into having additional data in the Zarstore that would tell when we downloaded the data that went into each array value and what the timestamp, when we downloaded it and where we got it. So at least if you kept that record at the time that you were accessing the Zarstore, you would know. But again, if you didn't bother to like store that information, you know, it might disappear unless we have this sort of versioning that helps us with that question.
Just a quick note, I'd be shocked if Earth Mover Array Lake doesn't offer you time travel. Like it almost certainly solves that
Well,
problem if you wanted to.
Right. So it's basically there, it's modeled after like a Git repository. So that's the idea behind the versioning. But if you have a petabyte data store, doing that comparison between, you know, one version and another version of a petabyte store might be tricky.
Sorry, it's like this is actually pretty common in like the database field. Like they're just storing diffs. It's pretty easy to if you have a petabyte, like only the diffs are managed. It's not
So
terrible,
what's-
hard to do.
Yes. So I think we would have to defer to Array Lake and how they have not, we don't know how they're doing things, and we don't know if they are able to produce that.
If you look at similar technologies in the data space like Delta Lake or Iceberg or Hoodie, all of them are very similar to architecture and all of them offer the exact same things.
Oh,
This is
wow.
very common, for example, in a bank. They want to look, hey, what was my
Yes.
records look like last January 3rd when I'm running my regulatory analysis? And it's the technology is exactly the same. So I suspect you'll have exactly the functionality you want.
That would certainly be great if they had it. Yeah.
And I apologize in advance for this question, but have you perhaps entertained the idea that maybe Czar is just maybe not the right solution for this, because you're appending data to a file which by its nature you want to be archival, and maybe the answer is more to actually add data in a way that doesn't actually change any data and instead adds new artifacts to your data.
We're from the Giovanni team, and historically Giovanni, in order to provide services across a broad variety of data sets, we have always stored a second copy of the original data for two reasons. One, for performance, and the second, to normalize the metadata. So the Zarstores that we actually deal with are not just exact copies of the metadata and file structure of the original files. We do things to normalize, for example, the order of the dimensions, and make sure that our longitudes are always between -180 and 180 instead of 0 and 360. So for our use case, the original archival data is often not appropriate for reasons above and beyond performance.
Yeah, so to that end, Matt, and I think this is, when we start a new project or whatnot, very often the first thing that we do is download all the data and put it in a better format to be dealing with the data. And part of this effort has come out of the fact that we have projects that are doing that, like Giovanni and elsewhere, where they have data that's useful to them in a format that's really good for time series analysis. And we just want to make that available. So it's not necessarily the archival use case, but it is important to kind of keep that up to date. And we would love to be able to publish what we have in these more cloud optimized formats and to keep it up to date so that people can come in and use it and not have to do that step one of, okay, I'm going to download the whole thing and put it in a better form, or move the whole thing into my cloud system and duplicate it all.
Okay, and I think it is time for our last presentation. All right. Okay, I hope I haven't messed. Where is it? I don't know how to get out of. Oh, you have. I hit
No, it's
escape.
going crazy.
Okay, perfect.
So it should just be Okay.
So my name is Aaron Fries. I come from the NASA Land Processes DAC, where I'm the science coordination lead, basically meaning that I'm kind of an interface between data archive activities and our user community. What I'm talking about today is way less novel than what we've been discussing today, but I just didn't want the discussion about cloud optimized formats to stop at Zar. One thing to point out, as of right now, the only cloud optimized data format that's available through EOSDIS in a public form is cloud optimized GeoTIFFs. And so, yeah, we got a whopping 5, and all of them are actually data sets that the LPDAC supports right now. And I think there's actually some that are in a not public space, not tagged correctly. Okay, so of the GeoTIFFs down there, which 416 is different than yours number, there could be COGs there as well. So it's a format that's being currently used as an archive format within EOSDIS. Also, I think GeoTIFF was approved by our standards and coordination office as a approved data format. We have kind of a process for data formats and metadata and the like. And so back in 2019, GeoTIFF was approved kind of by default. We just assumed that COG fit that mold, but they are kind of reviewing, at least with the COG flag. And as of July 13th, it's under review. I don't see any problems with it getting through. Also, we have a developer production guide that we as DACs can hand out to data producers that has guidance and recommendations on producing data products. And COG has some language, I think, in version 1, but it's got way stronger language in the version 2 that's coming out hopefully pretty soon. So we do have backing as an archival format, I guess, for COG files. So why COGs? COGs are GeoTIFFs, so they just basically work, which is excellent for the vast majority of at least the LPDACs user base who are still very much in this download model. The COGs have actually went through kind of they have an internal organization now that allows for efficient access of those data in the cloud. So you get the benefit in the cloud, but it's still a format that people recognize, that people can use really without having to think twice about it. So that backwards capability or compatibility is very essential to our user community. A couple of the features, and I mean, like I said, this is not novel stuff. These are kind of standing on the shoulders of giants here, people who have talked about this before in much better terms. But a couple of the features is kind of a reorganization of the internal metadata that essentially brings the information that tells you where things are in the file up to the top of the metadata header. So that you can make efficient reads and know where that information is within that file. And this is kind of a common strategy, I think, across all cloud optimized data formats. And then part of that also is, or the information contained in those headers is the internal tiling locations, and then also overviews or kind of coarser versions of the data that you're looking at. So again, the internal tiling, we're not having to read row by row anymore. We're reading individual tiles so that when you do submit, say, a request for an area within this happy face, I'm not getting I don't have to read the entire file. I just get basically through that read of the metadata. It knows where to look, at least the utility that I'm using. Just grabs those 4 tiles that I'm basically interested in, and then I'm often working with that data in my environment. Internal overviews. I mean, this is maybe not at a pixel by pixel analysis realm, but if you are working from something like a web interface and you're looking and navigating throughout a map, having higher overviews is important for performance. And it's not until you really kind of zoom into that base spatial level that you want to see the actual raw data value. So this adds additional performance, at least at those higher spatial levels. I think, Patrick, you were involved in this study, I believe, and COGs are just kind of fast. You know, when you're working with individual pieces within the file, they're fast. They're transferring fewer bytes, and so just really in general, they are very performant for your workflows. And then that backwards compatibility or client support, it's all there. Whatever you used with the GeoTIFF, you can use with the COG file. So ArcGIS, QGIS, very big applications that are used in our user community, ERDAS, NV, multiple, or there's plenty of support in Python and R here as well. So we have plenty of support for these files. Taking a little sidestep, Appears is starting to adopt a new pathway using these data. So if you're not familiar with Appears, it stands for Application for Extracting, Exploring, Analysis Ready Samples. And essentially what Appears does is reaches into the archive to get data upon request, and will kind of create or will give you a kind of a spatially subsetted or aggregated version of the data that's been clipped to your area of interest. It will build some kind of exploratory graphs for you and give it to you in a COG format or a NetCDF file format. And then those recipes are kind of stored so that you could then rerun those or share those recipes with users and rerun it through the application so you can have the same results. But we've started to work with at least COG files that we have been asked to introduce. And so the Harmonized Landsat Sentinel data collection hosted by the LPDAC has been integrated recently into Appears. We're also dealing with some other COG files through EcoStress and also through a USGS collection called the Landsat Analysis Ready Data. And so we're not replacing our pipeline by any means. Our original pipeline leverages OpenDAP, leverages the OpenDAP's ability to read into NetCDF files or HDF5 files and give us variable subsetting and bring that back to the system so we can return that to our users. We're leveraging in the COG kind of pathway, I mean, utilities that are kind of openly available in the Python environment, things like RealXArray and Clip to make those kind of variable subsetting and spatial subsetting capabilities, or make those abilities available through Appears and using things like the stack APIs and the CMR API to find those assets that we're interested in extracting for. Some of the lessons that we've learned, I don't think these are really, I mean, this is more, we just went at it and ran into these things that were already defined. But so download in place versus in place. We initially worked with our Earth data collection, right? And that requires authentication. So we had that figured out, but then we started working with the USGS collection, which is a requester pays bucket. And so we had to kind of shift a little things there and be a little bit more aware of costs coming through in that scenario. File metadata versus band metadata. We've noticed that when we initially started saying that we had COG files, that we were actually not producing valid COGs. And so, and also we were placing metadata in some wrong places so that utilities like RealXArray weren't picking up attributes like scale factor and offsets. And so we had some figured out where to place that and when to place it. And then, of course, there's no in-place modification. So the COG file basically you have to have that order of operations correct to create a cog file, or else the placement of the bytes are not defined correctly in that metadata file. Cog for everything. No, is the short answer. It's great for 2D data, and I would probably, I mean, there's the ability to add a third dimension. I personally don't like adding the third dimension, and so it's fantastic for that. It's, if you're okay with having multiple files, that's a, I mean, I don't know if that's a philosophy thing, but I'm okay with it. Tiled products, it works great for us. I've in kind of putting this presentation together, I saw multiple videos of people, I mean, having global files essentially acting as their database that they were pulling from, and they were quite happy with the responsiveness of that workflow. So theoretically, or I think in practice, you can create global cog files and work with it effectively. And then the backwards compatibility, touched on that. Love that. Spectroscopy data, this kind of goes into the third dimension, having multiple or several hundred spectral bands associated with the cog file. It gets a little unwieldy and not really hard to use those files for the purposes of spectroscopy, which is slightly, I think, different than multispectral workflows. High temporal frequency goes back to the three-dimensional stuff. Self-describing, there is self-describing metadata in cog files. It's just not nearly as robust as HDF5 files and NetCDF files, and then no updates in place as well. So this is also, I mean, I got kind of pieces pulled together here. These are kind of examples that I ran into early on. So for those data users who are unfamiliar, I guess, with these spaces a little bit, this hopefully will help out. It's something I ran into when I first kind of entered into the space. There's kind of three examples here, and there's probably multiple more out there that I'm not addressing here. These were just kind of in my orbit when I started playing around with cog files. And we have three examples of basically kind of bucket policies, I think is the right terms. AWS Open Data, the way NASA Earth Data Cloud kind of works, and then also the way USGS in AWS has set things up. AWS Open Data, that data is just free, open, access it anytime, anywhere, no authentication, no anything. You can download it, you can access it in the cloud, it doesn't matter. You can do whatever you want. And it makes it very easy. And this code, of course, is super small, sorry, and probably a little bit more complicated than it needs to be for a presentation. But open data, fantastic. But it's not necessarily the same process that you would use, say, with Earth Data Cloud, right? We have authentication that we have to pass. We have to get credentials and pass those into a session that then proves that you're an Earth Data login user. And plus, our data can only be used in US West 2. So if you're doing any sort of direct S3 access, you have to be in US West 2 to do that. So there's no crossing that region boundary in AWS. AWS for the USGS cloud is a request or pays model. So their buckets have been set to a request or pays policy, which means that you can still access this data for free in US West 2. You have to pay for requests going on, but the transfer of data from into your environments is nothing. But you can also access this from any other region within AWS. And I apologize, this is very AWS centric. So, so yeah, users can access this data for free in US West 2. But if you are accessing the data out of region, you're paying for that egress, you're paying for requests, and even within region, if you're accessing that data, you're paying for requests made. And so those are just some things to be aware of, I guess, or to take into when you're building out some workflows that are using cogs, and I think probably other data formats to be considered. That kind of finishes up. Here's some resources that I find very useful or have had a part in building out the HLS data resources from our GitHub. Uses cloud optimized geotiffs. A lot of those in our resources have been developed from resources from the Pangeo community, specifically Rich Inback and Scott Henderson. They got some good COG best practices for not only just single file uses or access patterns, but also things using Dask. And so some resources if you're interested in using COG files in a Python environment specifically. And I'll finish there.
Thanks, Aaron. Yeah, no, just like an FYI to everybody, the cloud optimized geotiff standard, as of 5 days ago, is actually now an OGC standard. It was published earlier.
Sweet. Nailed it.
Okay, if there are no more questions right now, we've got about 15 minutes before lunch. So I guess what's everybody's burning questions they want to talk about to do with cloud optimized formats and NASA and everybody else's data? I feel like people like Doug have opinions. Oh, and everybody else. I'm going to go this way first.
Yes, hi, Alexander Yanek from HDF Group. I just want to plug in my session on Thursday, 4:30, about cloud optimized HDF5 files. I think that a lot of issues that Owen mentioned could be resolved with such files. And so if you can stop by, that's great. But it is possible to create cloud optimized HDF5 files in much the same way that they talk about COGS. And so I think that can help EOSDIS in many ways. So that's all.
I just want to say that this is all great information, and I hope that all the brilliant people sitting in this room are always thinking about the end users and how we need to access this data quickly, sometimes to refer back to situations where emergency managers or decision makers need to compare maybe what the land looked like a long time ago versus what it looks like today, and how flooding and stuff like that will impact people and residents differently as land use has gone on. And being focused in that area, people really do want to access NASA data. They really want to access NOAA data. They want to access all the government data that's out there. Most people don't even know that we have satellites that monitor the Earth. It's pretty sad out there when you talk to decision makers. And when you show them examples of imagery and data, they light up like, oh my gosh, how can I get access to that and use it? And for them, it's impossible. It's impossible. So the easier we can make it, and the easier we can point our web browsers to a domain or an area and pull in imagery or data into their systems so they can work with it, I think that's when we're really going to see a huge uptick in metrics for data access and things like that. So I'll always be the one on the ground trying to say, we need this. And I hope all the discussion in here is really focused on the efficiencies of data access and making sure we preserve the data as it is. But there are a lot of people out there that do want to use it.
Hi. Nobody's brought up Google Earth Engine. So I think there's cogs in there. I don't know if you could just speak about that a little bit.
What I'll say is Google Earth Engine is a user of our data from a DAC perspective. And what they do afterwards, whether they're converting it to a cog or whatever format they do, is on them. So I think as DACs I think some have better relationships with GE than others, or at least being able to track metrics in some way. But LPDAC stance has been that they are essentially another data user, very big data user, but they are using our data.
Hi, I just wanted to thank you, the gentleman, for all the things that you said. And I wanted to do a little plug of NASA RSET, which is the Applied Sciences and Remote Sensing trainings that NASA provides. They do training. They've touched almost every country in the world, and they target decision and policymakers and applied science, like people in the world who are like disaster monitoring and doing, monitoring land processes changes and vegetation changes and all these things. I mean, of course, researchers as well, but they know that the people who are, needing the data immediately and are making a, direct positive impact and change in the world, like you were saying, like they may not even know where to start. So they provide trainings online and in person, and they've been doing this for, I don't remember how many years now, but they're really amazing. So if you don't know about them, or if you need information, check out NASA RSET on the website and direct your folks to take their trainings. Anybody can do it, and it's free. And they also post their videos on YouTube and stuff like that. Thanks.
We do have an online question directed to me. Are COGS used as an archival format at the LPDAC? Yes, for certain data products, yes. Specifically harmonized Landsat Sentinel data.
This is somewhat unrelated, but everyone, I'm Matt, I work on DASK, I'm a Pangeo person. I think what we've learned is that like managing millions of files in S3 and providing transactional and consistent and archival access to them is like a fun, challenging technical problem. Fortunately, you are not the first group to address this problem. There's lots of other communities in the world that have addressed this exact same problem. I think what's great about the growth of the new technology stuff that I'm seeing in the geosciences space, that it's no longer just geoscience specific. People are using more standard technologies across other domains. So I'm kind of curious, as people are thinking about new technologies, new stacks that they're playing with, are they also reaching out to biomedical, to business, to banking, to other spaces that have actually solved or are in the process of solving a lot of these same problems? It's fun seeing Zar, which really came out in the geosciences space, now being used by a lot of biomedical spaces as well. It's super exciting. It's being used in finance. That's super exciting. That's a space where I think this group has been really a front runner in adopting new technology. There are some spaces where this group is behind, and it can learn from other things. Consistent access to S3 is one. So I think there's like, I think a lot of learning that people can do in this space if they reach outside of people in this room to other groups. So that's my shtick. Sorry, thanks.
Bruce Wilson, ORNL DAC number 1+1 to your comment. Thank you. A couple of comments. ORNL DAC is actually converting anything that's coming in as GeoTIFF into cloud optimized GeoTIFF. That there's a little bit of a problem if you cloud optimize something and don't put in the metadata, did you really cloud optimized it? And that's a piece that we still have to solve here on that. To your point, yes, Google Earth Engine does make use of GeoTIFF. I think GEE is an interesting challenge for us. One of the things that I often do at for something like AGU is I walk the poster hall and talk to people who are publishing or done science. So tell me what worked well for you. Tell me where you ran into the challenge. And one of the consistent things that I heard at AGU last year was I had a real hard time getting at this data until I found it in Google Earth Engine. and then asking some questions. Well, did you understand some of the, no, they don't understand any of the provenance about, how footprint level JEDI data was converted into a 50-meter GeoTIFF. Kind of didn't care. So I think that's one of these things that's a challenge for us, is what do we expose to the user? Exactly what Aaron is talking about. And I loved your summary of where cloud optimized GeoTIFF is good and not good. Absolutely. But how do we continue to do this sort of thing? Make the easy button there for the user. So, oh yeah, I found it in Earth Data and it was easy. And that's the answer that we're trying to get at. And everybody's working towards it, but just reminding us that that's the goal that we're after here.
Keeping me exercised.
Yeah, so this question is for Christine, and forgive me if this is really ignorant. Haven't worked directly with Zar data or any of those kinds of stories, but your presentation seems to be focused on worrying about keeping the Zarstore itself, provenance of that, and snapshotting and making sure the users getting they're seeing the same thing consistently as they maybe run it, different things against it. But I wonder if, starting from the Zar point, I wonder if it's better to look at it from a different direction. I mean, and maybe you guys have already thought of this, but let's say a user comes in and they say, I want to evaluate this parameter, from this collection across this time, or whatever the case may be, and that but then there's actually an index that indexes, that list of results they returned from a CMR query into a location in Zar, and then so that there's an abstraction, a user comes in and so that list doesn't change of the actual archived granules. You can update the Zar blob and then update that index as you go forward. But as long as you're indexed from your granule into some location in Zar, and that's kept up to date, then it really doesn't matter so much if the Zar blob changes. I mean, maybe you guys have already been down this road. I don't know.
So I think what you're touching on makes a great deal of sense, except for the way Zar is structured. So Zar uses implicit indexing. Is that sort of the term I want to use, I think. So if you saw in that example, there was chunk 0.0.0. You can't name it anything else or put it anywhere else. It must be in that exact location, 0.0.0. So if you get updated data, you must update it in that location. You can't put it somewhere else. So when you get information about a Zarstore, you really get just that top level location, the top of that directory structure, and then finding any data underneath of that is just done because you know what your array index is. So either you take the array lake approach, that style of approach where you have something that does store specific locations of chunks for each version and move away from that Zar sort of implicit indexing, or you're kind of, if you use straight up Zar, you're kind of stuck, to the best of my knowledge, but there are probably other people in here who might know better than I do. Okay.
Well, I think what you're describing is essentially aggregating data on a variable from multiple files. Is that basically what you're saying?
Right. I'm assuming that's what they're doing.
Because that's what the guy with the noisy laptop, when he mentioned Kerchang. And by the way, since he's not here, I know he likes to, use Zar on his laptop. That's what you get when you store Zar on your laptop. So, but just saying. So basically, Kerchang gives you this aggregation across essentially a single variable across multiple files. So I think it's doable, given that things are uniform right now in terms of chunking and things. You could, yeah, you could combine metadata from these things into JSON that would combine them.
It does get a little tricky though if you have hundreds of thousands of files. So the JSON becomes huge. So that's why sometimes people use databases. There are, yeah.
Like literally this exact same thing happened with Parquet. People are probably familiar with Parquet as a data file format. It's a tabular data file format, looks very much like Czar. We use it all the time. It became challenging to update little sections of it in the cloud because transactional access in the cloud is hard. What happened is people liked that format, but they wanted a different metadata versioning of that format. And that created a new generation of file formats called Delta Lake by Databricks, Iceberg by Tabular, and Hoodie by I forget who. They all still use the Parquet representation, the Parquet formatting of the individual bytes and individual chunks, but they add on different metadata on top of it. So it's still Parquet represented, but there's a new system that does more intelligent tracking. Array Lake is exactly the same thing as something like one of these new formats, but using Czar kind of underneath the hood in that same mechanism. So you guys are kind of going along the same path the tabular people went on. You're asking exactly the same questions, running into exactly the same problems of how do I get transactional ACID access to a million things in S3 while updating them. So again, this is a very common story we've seen in other industries. Array Lake seems like it's going down the path that has worked in other spaces before. Like other people could make other metadata systems also around Czar. That seems to work well, or around NetCDF or around HDF, right? The chunking of the data on a per chunk basis, the representation there is one thing. And how we sort of construct interesting metadata around that is another question that's open. But we can keep the same representation on a per bit based on per chunk basis. And that makes things archivally much nicer.
I think I've got one more question there, and then it's going to be lunchtime. Oh, two more. Okay, last two.
Just a note to defend Rich's honor since he's not here and his noisy laptop. No, on the chunk side, both of you mentioned the concept of like extremely large JSON files when we have a large number of reference files. But we're working towards solving that as well with using Parquet as our index file or our reference so that we can stream locations and we don't have to load this entire JSON blob into memory. So yeah, so hope like that's a solved problem. It's still relatively untested, but we're able to make effective chunk indexes for millions of files that work pretty well.
Okay, then. Well. Okay, with that, then I think it's lunchtime. Thank you, everybody, for coming.